Okay, hello everyone. Welcome to Happy Hour with Architects. Today I'm super excited to host two stars in computer architecture. Let me introduce our guests. Our first guest is Christina Delimitrou. She's an assistant professor at Cornell University, and she's well known for her work on data center performance and resource management. She is undoubtedly one of the rising stars in computer architecture. She has received numerous awards for her work, including the TCCA Young Architect Award. This award honors her exceptional leadership and contributions in data center design. Welcome, Christina.
Thank you very much.
Our second guest is Partha Ranganathan. He is the Vice President and Engineering Fellow at Google. He's responsible for designing Google's next generation systems and data centers. He has been the leader in innovating large data centers based on total cost of ownership and energy efficiency, which now actually has become the norm. He has received numerous Rockstar Awards, including the highly prestigious Maurice Wilkes Award. For people who don't know, Maurice Wilkes built one of the first stored program computers at SAC in 1949. And Partha received this award for his pioneer work in servers and disaggregated systems. So welcome, Partha. I really appreciate you two finding some time to join the discussion today.
Yeah, pleasure to be here. Thanks for having us, Samira.
Yeah, thanks for organizing.
No, it's my pleasure. So for the first, just to start off, I guess I will just ask about how you started working on data center architecture. And I guess let's start with Christina.
Sure. So it's been, I guess, almost 11 years at this point. It goes by pretty quickly. So I did my undergrad in Athens, the National Technical University of Athens. And then from there, I went to Stanford. And when I started, so 2010, cloud computing wasn't as big of a research topic in academia. Obviously, data centers already existed, but it was when it was getting started in academia. So more people were starting to get involved. And we had this collaboration with Microsoft Research that was on workload modeling and generation. So essentially, what we were trying to do was collect traces from production applications and then have a way to mine those traces to see what locality there is across the storage hierarchy and across the network topology, and have a generator that captures those characteristics and regenerates them. So I mean, that line of work continued for some time, but the side effect of that was that as I was looking through the traces, I saw that the utilization of cloud servers was much lower than I expected it to be. So I expected that given that there is plenty of user load, the utilization would be close to saturation. And what I saw was like 10, 15%. So that kind of started this line of work of, is that the right way of managing resources? What are the reasons behind this low utilization and how we can improve it? So I started looking more into resource management, ways to avoid interference. So if you have multi-tenancy, you want to avoid interference between co-scheduled applications, what's the best way to do that? And I guess a happy coincidence at the time was that I was taking a class, this was back when I was taking classes, on mining massive data sets. So this was a class that Yuri Leskovich was teaching at Stanford. So I think it was his first year as well. And part of the class was introducing the Netflix challenge, which was, for people that may not be aware of it, it was this competition that Netflix ran a few years ago now on across different academic and industrial teams to improve their recommendation algorithm. And the winning team, Belcore, proposed, among other algorithms, collaborative filtering, which essentially was this black box technique that was trying to find similarities between different users and their movie preferences. So I remember being in that lecture and saying, okay, that problem is very similar to the problem that we're trying to solve, because what we're trying to do is figure out what are the resource requirements of these applications that the system hasn't necessarily seen before. And we don't have the luxury of profiling this application in detail. So that's how the line of work of applying ML to cluster management started, and that has since evolved to like more scalable scheduling, looking at hardware acceleration, looking at newer programming models, but that's how it started.
Yeah, that's a great story.
And I love the collaborative filtering work. I still remember reading that paper. Very nice work, Christina. So for me, I think, actually, I would say I've always been interested in systems. And so I think it's good to look at how the entire architecture works to solve a problem. But I would say the place where it probably started is in my first internship. So I just finished my master's. I went to digital equipment for an internship. And at that time, I was working on memory consistency models. So Sarita Adve was my advisor. So the architects here will see why memory consistency model was what I was working on. But then I went and did my internship, and it was kind of really eye-opening to me about how small the work I was doing. So when I was trying to describe my work, I would say, hey, I'm working on memory consistency models. And I realized there's this huge space for computer architects to play. And there is like data centers, and there is servers, and within servers, there is systems, and within systems, there are system balance. And then within that, there is a processor, and within processor, there is a memory subsystem. And somewhere in there was this memory consistency model, right? And so to me, it was really interesting to see the big picture there. And for the students who watch this video later on, I think that's really one of the things I encourage people to do with internships or visiting sabbaticals or whatever, is you really kind of open your eyes to the possibilities that you do. And it was very refreshing. So I went back, and then I was like, I want to work more on the system side. And so then I pivoted my thesis to looking at architectures for databases and media processing workloads and so on. I spent a lot of time understanding Oracle, building simulators for multiprocessors, doing a bunch of stuff. And so that's kind of where things started. And then after my PhD, I decided to take a break and go do power management for a while. And I did a lot of stuff with handhelds. And once again, when I was working on handhelds, I realized, look, the fundamental things that are causing power problems here have an equivalent analog in data centers as well. And I still remember when I first started doing power management for data centers, literally people would laugh because they would be like, hey, who cares? Electricity, we have a wire. It's not like a battery or something that's going on, right? And I was pretty lucky because I got in very early. And then 2 years later, data center power management and electricity costs was one of the biggest things. And then we invented power capping. We invented the first benchmark for measuring power, joule sort and spec power and PUE. And again, funny story, I tell my kids, my kids are teenagers. And so I have to constantly tell them stuff to impress them on why they should look up to their dad. And I'll tell you, it doesn't work all the time. And I usually tell them I'm like an world gold medalist. And they ask me, what did you get a gold medal for? And it turns out if you invent a benchmark, the first time you get to win it as well. So we actually have this really nice world gold medal, joule sort winner. And so we were the first winners of joule sort. So it's I still have it in my awards trophy a little bit. So I moved to data center power, and then we started looking at from there disaggregated servers and data-centric data centers. And of course, at Google, I got the chance to work with Luis and Urs on writing the data center as a computer book as well. And so I've been doing stuff. So, but everything started off with that internship and the imposter syndrome of like, wow, I do this small thing in this big universe. There's a PhD comic that actually shows how your PhD is this dot on a circle. So that's kind of the feeling there.
That's a great story. Like, I think Christina mentioned her like taking inspiration from her class and lectures. And you mentioned that like just by looking at the big picture from memory consistency to going bigger and bigger, how that helped. But I guess I would like to point out that most probably you still had to use very similar insights for memory and caching, but at a greater scale, right?
Yeah, no, everything is like the same. So you just have to reinvent the same stuff in different ways.
So I guess one follow-up question I have is like the data center architecture itself is not that old, right? Like we are talking about maybe 2004-5 when it we are really concerned about power and the main resource management. But within like 10, 15 years, we are now a very different stage in the data center architecture, or even, I guess, as a whole computer architecture. So how do you see the change from, let's say, 2005 to now? Like, how is it different? Like, how is just the data center architecture different?
Yeah, I can take a stab at it, and then maybe Christina, you want to jump in. I think you have a very different perspective than I do in this as well. I still remember the day when we didn't even have data centers, right? We had cluster rooms or data center closets, and a computer room was literally a closet in or a room in a building and stuff like that. And I think the internet boom was very significant. So in the 2000s, we had a bunch of really back-end infrastructure. So you had the Sun computers kind of saying, hey, we are the dot in the .com or whatever their slogan was at that time, right? And so I think that was a pretty big inflection point. And then we continued to keep building data centers, and then the end of Dennard scaling with power becoming important ended up making power important. And I think the next big inflection really was when Google came along and said, we are going to rethink data centers, and we're going to think of the entire data center as a computer, right? And we were doing the same thing at HP as well. And this notion, you can think of the data center as one big computer, and the power delivery is equivalent to the power supply, and the cooling is equivalent to the fan, and then the network and all of that together is the computer, and there's an operating system, and you're looking at that. That was, I think, a pretty big pivotal point as well. And so that was one set of epoch, and you had all of these things, and then Facebook and Microsoft and others did that as well. And then the third inflection point I see really is around cloud taking off. And all of a sudden, you have a merging of all these data center closets, and you have everybody kind of starting to initially use cloud just as a way to automate things and make things easier to manage. But now cloud has become this place where you get early access to really cutting edge technology. And it becomes like a fundamental part of companies digitizing their business, because all of a sudden you have very retail companies kind of doing digital stuff, and cloud is the place where you can get the latest machine learning, things of that kind. So to me, those are the three big epochs, at least just in my career. And I think we are now in current day where we are starting to look ahead to what is the future of the data center. And I see us again rethinking a lot of assumptions. So I have a feeling in another 5 years, we'll be looking back and saying there was this inflection point where end of Moore's law, accelerators, persistent memory, automation, new battery technologies, and we ended up with edge is another place, and we ended up with a completely different stuff. So I think we are in the middle of the fourth inflection by my count.
Yeah, I mean, that was a great way to summarize it. So, I mean, if you look at what data centers look like internally, they're not the first systems that are large scale. We had HPC before. But the difference between HPC and data centers is that HPC is specialized equipment and data centers are commodity. So in some ways, they are more similar to the traditional architecture systems that we're used to seeing, like what you would have in a desktop or laptop machine, but obviously with many more resources and streamlined for the applications that the data center is running. But yeah, they were not the first systems that were at that scale. And what you've seen over the past couple of years, 3 to 5 years, is that we're kind of moving away from that commodity equipment approach, and you see more specialization in the data center. So primarily in the hardware, but also in the way applications are written. So again, the cloud used to be something where anyone could go and run whatever application they wanted. And right now there's more formulaic expressions on how people write applications, the programming frameworks that they should use so that they run well on the underlying hardware. And you see a lot more specialization and diversity in the hardware as well. So we'll see where it converges. It's kind of like going back and forth between commodity and specialization.
So I guess what I would like to know that, like, how the Moore's law is ending. So you both mentioned that, but how that is kind of changing the landscape of data centers.
Sure, I can start. So like if you look at what a server looked like, I don't know, like 5 or 8 years ago, it looked like a multi-socket machine, typically 2 sockets. That's usually the sweet spot, few tens of cores, gigabytes of memory. And right now, if you look at what a server looks like, most likely it will have an accelerator. If the data center is optimizing for ML, if it has a public cloud component, it will have some ML accelerator, maybe a network accelerator, maybe a database accelerator. So you see much more heterogeneity, which obviously it's there for a good reason, because Moore's law is ending. There's a lot of performance and power benefits, but it has a negative side, which, you know, the programmability side of accelerators, that's very well known, but it has a complexity side as well. So it's not as easy for people to know how to handle these accelerators, especially when you talk about exposing them to the end cloud user, not just the people that program them internally. So there's a big challenge on, you know, what's the best way to run applications on these systems? What's the best way to manage resources for these systems? If you want to support multi-tenancy on accelerators, how do you go about doing that? But I think it's a very exciting time because there's a lot more interaction between the hardware and the software. I was actually attending HotOS, so Partha was in another panel there, which was very interesting. So I attended HotOS a few years back, and most of the discussion was like microkernels, OS optimizations, OS scheduling, libraries. So interesting, but not as interesting for me. And this year, I was actually impressed by how much people were asking about hardware, and they wanted to learn more about how hardware works, where hardware is going, how to program it, how to write applications for it. So I think, you know, there is a downside to this diversity and heterogeneity in hardware, but there is an upside as well in that there's much more collaboration and much more co-design between hardware and software.
Yeah, no, I think I do see the same thing you see, Christina, about, I think very paradoxically, the end of Moore's law is actually creating the most exciting time for computer architects that I've ever seen. And it's interesting how there are first order effects and second order effects and third order effects, and all of them are very, very interesting, right? So Christina talked about accelerators and co-design. I mean, the machine learning accelerators, I look at video accelerators. We just published a paper on video accelerators, and I'm very excited. I think there's a lot of opportunities around where we see, I mean, this particular conversation. I noticed how Christina just very casually said, I attended HotOS, and I'm like, wait, you watched videos, right? And there is so much of video. Yeah, there's so much of video in our lives right now, and all of this video is running on some computer architecture that we get to design, and the VCU that we looked at runs all of Google Hangouts. So every time I'm on a video, we are like, look, computer architecture here at work here. A lot of interesting stuff with co-design that Christina alluded to, and honestly, I think we are at the beginning of this, so there's a whole bunch more left. But then I look at second order effects, and I say, how do we democratize accelerator design? And we have this conversation at Google all the time, and we have it in academia as well. It takes so much money to build an accelerator. It takes so much effort to deeply understand a customer workload and then try to figure out how to architect it and what kind of stuff that we do. And so I'm very, very intrigued by some of the whole open source hardware stuff. I mean, RISC-V is an example, but it's not just the ISA, right? I think it's this notion of how do we automate? We've been using machine learning for hardware design, and I think that's very interesting as well. But then you also have some other third order effects as well, which is really around, if I look at security, if I look at reliability, just in the last few years, all the side channel attacks that we have seen are kind of an expression of people starting to exploit the complexity that we have introduced, right? As Moore's law slows down, we have to get more and more complex about our designs, and that leaves us open to different kinds of vulnerabilities, and those are opportunities. Same thing with reliability. We are seeing some very interesting trends where the number of errors, we call them corrupt execution errors, they are increasing, and it turns out it's probably the technology scaling, but also the complexity. And so that's, again, a new interesting problem for computer architects. We've always been looking at that, but how do you do it at volume for not just a few high-end tandem supercomputers with dual modular redundancy, but actually do it for everybody's systems, right? And then another example of a more insidious side effect is this whole software-defined infrastructure. And the notion that hardware doesn't present itself as hardware, but hardware is presented by a layer of software. scheduling software that manages it. And then you can transparently say schedule between a GPU and a TPU, or a server type 1 and server type 2. And again, I'm sure Christina has a lot of thoughts on this. And being able to now think about, architects have to really reason about infrastructure as a service, not just the hardware, because that's how you push on Moore's law as well. So that's very interesting. So what started off as just saying, hey, a scaling law that Dennard invented in 1969 died. And because of that, I have to figure out how to get more out of my transistors, just has profound implications. And then the last bit I will say is, if I look at the demand side, I was seeing this data from OpenAI, and they actually have an updated version. And if you extrapolate it, the growth in OpenAI's computing demand is 10x every year. And to me, that's just mind-blowing. So we kind of, traditional Moore's law is 10x every 4 years, right? And the fact that we are so far behind on exponentials. And if I look at data, YouTube, the number of hours uploaded per minute is like, I don't know if it's at 600 or some big number right now. And it's at an exponential that's much faster than compute. So, and I look at some of the more interesting societal challenges, whether it's around machine learning for medicine or sustainability or COVID or whatever. I think underpinning all of that is an expectation that Moore's law continues. So I see a lot of pent up hunger, and I see all these opportunities open. So to me, as I said, paradoxically, the end of something actually has been an exciting opportunity for us as computer architects. Not that I'm complaining, it's good job security for all of us, right? So.
Yeah, that's a great point. I mean, for a long time, I don't want to say that architects were complacent, but what is that we say that you can solve all problems with another level of indirection, except for having too many levels of indirection. And I think we are at the point where we have probably too many levels of indirection as a way to handle complexity, but obviously that introduces a lot of inefficiency that is still there.
Yeah, and then one place where I always think there is a lot of inefficiency in layering is in the cache hierarchy, in the data hierarchy, right? And I often think that we have probably gone overboard. We have L1 caches, L2 caches, L3, L4, first level DRAM, second level new memory, third level non-volatile flash layer, and then disaggregated memory, disaggregated flash, storage, disaggregated storage. And you have this poor compute and these 15 layers of data there. So I sometimes think that maybe we should rethink that and see what we want to do then.
Mm-hmm. Yeah, that's a good point, especially if we're talking about cloud applications. They don't really need the 3 levels of cache anyway, because the data sets are so large that you go to main memory to begin.
So Partha mentioned about that because of Moore's law, the architects are designing all these different types of accelerators and other innovations. And that is kind of introducing changes in all layers of the system. I guess Christina also mentioned about hot OS, that even people are thinking how to rethink the kernel or rethink the scheduling or rethink the programming language to take advantage of these heterogeneous hardware. So I have an observation that as a hardware person, like it's very easy for me to say that because of these changes in the new hardware, these are the changes needed in the software stack. But how do we convince the software people that what exactly needs to be done, or how should we work together as a software hardware team to take on these challenges? So what would be your thoughts on that?
I think the software people understanding what hardware looks like and the hardware people understanding what applications run on that hardware is a great step forward, because even looking at conferences, there's a lot of papers where the application target is a microbenchmark, and that's not what will run on that hardware. Or from the software side, you kind of assume that the hardware is a black box, and it's not really a black box. There are aspects of it and design trade-offs that if you want your system to behave well, you need to know. So that's why I was happy to see the discussion in Hot OS, and that's why it's great to have venues like ASCLOS where you see both the hardware side and the software side. But obviously, again, there is modularity across the system stack, so there's a lot of lot of conversation that needs to happen for the two sides to understand each other.
I would probably take a slightly different approach to how I think about that. And I would even very respectfully submit, Samira, that maybe that's not the right question to ask, right? So because ultimately, if you start off asking, hey, how do I convince software to change? So to me, the right question to ask really is, what's the problem we are solving? So I work at Google, obviously, and I face this problem all the time, because how do I convince somebody writing web search who a whole bunch of users depend on, and there's like tons and tons of code, and they are making changes every 2 weeks and making big launches every 2 weeks, and I'm asking them to change, and it's a very intimidating place to be in for a hardware architect to look at. However, the way that has worked very well is to really say, what is the problem we can solve together, and be open to figuring out what is the simplest way to solving that problem. And if you look at the number of papers I've published in the last few years, many of them, and I would actually say a good majority of them, are what I would call software systems papers versus the classic hardware papers, right? Just in the last 2 years, I've had more OSDI papers than ISCA papers, for example. And so to me, it goes back again. You have a system problem you're solving. You have a customer problem, end user problem you're solving. And you go in and try to say how you want to solve it. And then at some point, you realize you're going to have to build hardware. And then it becomes exactly the point that Christina said, which is, what is the right way to provide abstractions and interfaces in a way that simplifies this problem on a sustainable long-term growth perspective? And there I would probably do a shout out to this really nice book that I read from John Ousterhout at Stanford, and it's called A Philosophy of Software Design. Mm-hmm. And the book actually goes into some really nice examples about, it's software, but it says, hey, here's how do you design classes in an object-oriented programming, and how do you decide what goes in a class, and what is the right interface, and what do you encapsulate, and what do you think about information leakage, and it's not that dissimilar from what we have to do when we do hardware-software co-design. We are basically drawing boxes, and we are saying, hey, should the interface be thin or thick, and what is the leakage that we want to see here? And how do we keep the surface area of the interface small enough so that it sustains over time, but still allows for opportunities and so on. And so that is how you kind of end up with that. And then when you go at it from, here's a problem statement, here is the solution, and then it's a co-design from the point of view of what is the right abstractions, then I have found that it gets a little easier, because you're no longer starting off with saying, hey, what is the minimum pain that you want to go through to make this amazing accelerator work? It becomes, we have this amazing accelerator, and what's the right way to do this with minimum pain, which is the same words repeated in a different order, but it's an interesting reframing that helps quite a bit.
Mm-hmm. Yeah, I agree. Actually, since Partha mentioned John's book, it is a great resource. I actually taught this short summer course a couple of years ago using that book. And what we did is I had a small group of students, and they were trying to build a microservices-based application from a monolith. So they really had to understand what's the right granularity of designing an application. And it was very interesting to see them not struggle, but like debate on what is the right granularity.
So I guess my follow-up question would be, given that we are saying that even the hardware architects needs to understand the systems problem and work together to solve it, Christina is mentioning about just in order to design the microservices, the students still have to know how to design the system software. So for architect students, like, what do you think is it would be the right skill set that they should require at this time? Like, it's like 20 years ago, like maybe memory consistency and caching, like just looking at a very small piece was enough, but maybe it's not true anymore. So I guess what would be your suggestion or advice to students who are currently looking for new topics and trying to acquire new skill set?
Yeah, that's a good question. So I teach an architecture class in the fall. And what I tell them, I think in the second lecture, is that if you were taking this 20 years ago, we would only go up until this point. And up until this point is discussing different ISAs. And now that is the second lecture, and then we'll move to 20 other topics. So like caching, memory hierarchy, storage, operating systems, networking, and all these things. So This will vary a lot depending on what's the research. If we're talking about graduate students, what's the research area of the student? But at least from my perspective, I think it's very important for students, in addition to architecture, to have a good knowledge of operating systems, a good knowledge of distributed systems, and a good knowledge of how applications are written. Now, that doesn't have to be in-depth knowledge of different programming languages, but at least how compilation works, how designing a large application works, which goes back to what John Osterhout's book was about. It's very difficult to do impactful work if you only understand one level of the system stack. You don't have to be an expert. You cannot be an expert in everything, but you at least should need to have a good understanding on what the software looks like that will run on that system and what's the operating system. So what's the interface between the hardware and the software?
Yeah. So well, first of all, in case Sarita watches this video, you should always learn memory consistency models. So I think it will never go out of fashion. So let's get that out of the way there. But I think Christina hit the answer, right? So so the way I encourage students to think about it is, again, this is the epiphany I had in my internship, is understand the impact you're having on the world ultimately. You could be working on a small table in a branch predictor, but you need to be able to look at what does it do to the end user's ultimate performance. And so in addition to kind of the academic rigor that Christina said, the only other thing I would add, yes, you should take compiler, operating system, distributed system courses, understand the stack. Trying to build something end to end and understanding the end-to-end outcomes, because oftentimes in our community, we focus on IPC, and I think it's fine, but IPC takes away a lot of stuff, right? And so what you want to do is, like with search, we focus on queries per second. With video, you look at, hey, how many videos have you transcoded? Or with gene sequencing, you're looking at the output, right? And so I always encourage people to take an application, and it doesn't have to be data center. It can be a phone where you're writing an app, but understand what the end result that touches the user is, and then work your way backward on, are you addressing what the requirements are? Oftentimes it's performance, or it's performance per watt, or it is reliability or manageability or whatever, right? So to me, that is the key thing. And almost all my most successful projects have been because I started there, and then I realized that it needed a very different approach. For example, when I started doing mobile power management, my goal was to say, hey, battery life at that time was like, and I'm dating myself here, I was working on this phone called an iPac. And this was from Compaq at that time. It was like the world's second handheld. We had this research prototype called HC, and then iPac was the first, one of the first commercial smartphones at that time. And I was trying to improve the battery life from going from a day to a week or whatever, right? And so when I looked at it, it turned out I thought we would end up with compute, the CPU, and I had a lot of computer architecture ideas on that. But when I looked at the problem, it turned out the display was 1/3 of the power, the wireless was 1/3 of the power, and CPU was 1/3 of the power. And knowing that gives you a very different perspective. And we ended up actually going to looking at display. And interestingly enough, as a computer architect, we studied display power management. And I was like, hey, look, I measured the display power. We kind of, because we are hardware people, you can disassemble it and put an oscilloscope and actually measure the power. And the power for the display was one constant line. And the power for the CPU was going up and down, right? And because, and so we got this really nice idea about what would voltage and frequency scaling look like for displays. And so we actually measured it, and it turned out that what we see on the screen is very different. Sometimes you have a small window, a big window, high resolution, low resolution. And so we came up with this very new area called energy-aware user interfaces. And we leveraged this new hardware technology called, at that time, OLEDs, because at that time, everybody was using CRT and so on, right? And so we said, hey, with this OLED, you have pixel-wide control, and you can actually adapt the power of your display to what the content is. And so that ended up taking the display power down by a factor of 4. And it is a very computer architecture thing, because there was a lot of hardware. We had to build prototypes. We were inspired by voltage and frequency scaling. And so we ended up doing that. And then once you did that, we solved Wi-Fi as well. And then CPU became 60% of the power. And then we ended up inventing Big Little, what is now called Big Little. But at that time, we worked on heterogeneous multi-cores, right? And so to me, the aha moment really is if you focus on the full system and you focus on what is the perceived value that we are delivering to the user, then automatically you're forced to learn all these things. And then I knew squat about display technology, but I worked with Kodak and I learned about how organic LEDs worked and what the display trends were. I learned about device drivers. I learned about industry trends and industry standards. So automatically you would learn that. So that's the only other thing I would add is have this relentless focus on what is the end user metric. And yes, use things like IPC and MPKI and all the other fun stuff that we like, but always go back and say, what will the end user be measuring, and try to see if you can take your work and meaningfully change that metric.
Yeah, that's a great advice. So do you have any comment on like the fact that sometimes in academia, it may not be possible to look at the whole application, or for example, you mentioned search, right? Or you also mentioned reliability. Many of these research is actually kind of hard to do in academia. So what suggestion would you give to students for that?
I'm actually going to say, I'm going to speak before Christina and put her on the spot a little bit, but I would say Christina has done a fantastic job, right? I mean, so I don't think it is hard in academia. It is, I mean, it is work, definitely, but there are good instances. I look at the microservices work, and I would say that's a great example of focusing on a full service and looking at stuff, right? So I think it's possible. It's just much harder. And this is where I think having the industry academia collaboration and trying to use touch points, those are very helpful. I already talked about internships as a way to do that. Visiting sabbaticals, we get some really smart people who have been, we've been very fortunate to get to visiting sabbaticals with us, Samira. And so I think those kind of things are very helpful as well. And but I think in general, it's hard, right? Even in industry, I don't get to go mess with web search just because I have an idea. So we always have to come up with models. So this is again a call to action, I would say, for people here, is to not have this distinction between industry and academia, but really try to think about how do we make our infrastructure modeling stuff as rigorous and real as possible. And there's a whole spectrum of options. And I honestly think even a small size cluster of 10 machines, 12 machines, is better than a single machine. And yes, it's not the same as 1,000 machines, but going from 1 to 12 gets you 80% of what you need to learn. And the last 20% we can take in other ways as well.
Yeah, I mean, I completely agree with Partha. So it's definitely challenging. I mean, having representative applications in academia has always been a problem, especially when you look at cloud systems. And since you mentioned the microservices work, so we started this work back in 2017, and I had to convince my students to spend about a year and a half building applications, which is not necessarily the most interesting research work to do. So I had to really sell it that, once you have these applications, there's all these research projects that you can do, and you're fostering a community that other people will contribute to, so you won't have to do everything yourself. But that does not mean that the applications that we open sourced are production applications, by no means. Like, of course, they're much more simplified versions to what you would find in a production system, but nonetheless, you do have the end-to-end performance metrics. You do see an application that runs distributed, is using components that are representative of what would run in a real system. And at least for the specific project, we did try to find wherever possible open source frameworks that were in use in production systems. So things like RPC frameworks, things like web servers or databases. And of course, the logic is going to be much more simplified to a production system. But even that is useful, is much more useful than having a micro benchmark or having something that is an individual tier. So, to students that might be listening, absolutely put the time in developing benchmarks. It might be quote unquote boring work in the short term, but it enables a lot of research projects in the long term.
And maybe the one thing I would also add is I think it's worthwhile to think about a community as well. And it ties in a few things here. So I talked about open source hardware earlier. We talked about what should students learn, so on as well. And just having an awareness of where are the places where the industry is standardizing, and being aware of big open source frameworks. Like right now you have Open Compute, you have the CHIPS Alliance, and the CHIPS Alliance has a bunch of IP blocks. We do this a little bit with, say, something like in Simulator, we have GemFi or Simple Scalar. But as a community, I think we have an opportunity to create ecosystems which are modular, where somebody can download the entire ecosystem and then play with one module and then contribute it back, and then the community gets richer and richer. So think of Linux, right? I mean, that's how we have Linux or Android or Anthos or Kubernetes or Chrome or all of these things. And I think we have an opportunity, especially with open source hardware and so on, to start thinking about that level of community building as well. And again, we don't teach students this as much, and this is something that I think it would be great for everybody to have an awareness of, hey, CXL is an industry standard, or AXI is how a lot of stuff ties into an ARM CPU, and be able to be aware of that and then build things in a way that it can easily, without friction, plug into the broader ecosystem. And one example is the prefetching championship that we have. I've been actually very surprised by how seamless these contests have run. And mainly because we have this infrastructure, and then you have a pluggable module that you can bring in. And then all of a sudden, to Christina's point, you don't have to have a poor graduate student spend 2 years of their life building infrastructure. They can build on top of other shoulders, and then they can just put their module and they can put it in and so on. So this notion of community building and open source hardware, I think is, again, very interesting, and I don't think we have done enough. So there's something probably to look at there.
Yeah, that's a great point. And if I can add one thing to that is, once you have a community, it helps a lot with reproducibility as well, which is an issue that we've had in the architecture community. And it's something that, you know, software communities have focused on for a long time. And if you see PL conferences, even OS conferences, they have a big component on making sure that the papers, the work is reproducible. And it's great to see that the architecture community is also starting to focus on that, but having open source projects that people can build on, make sure that the work is reproducible.
I completely agree with everything you have said. So I would say that in our architecture community, maybe in last 20 years, we are kind of trying to take these out of order x86 processors, and we are trying to improve upon them. So maybe Simulator was a good choice at that time, but currently when there are 10 accelerators being designed in Google, Microsoft, Amazon, and things are changing so fast, I don't think we actually have enough time to even build the simulator, because the next accelerator would be already out there. So I clearly see the benefit of these open source hardware, but I guess unfortunately, it has not been caught up. It has not caught up yet, but that also means that it may be our responsibility to start that.
I mean, hardware is always slower to build than software, actually. It takes more.
So in terms of open source hardware, I completely agree that if we modularize it, it would be easier to actually both reproduce and accelerate the innovation. So one particular thing I want to ask regarding that, because nowadays the big companies are building their own chips. So the model kind of changed now. Like, it's not Intel building something and then they're selling it to customers, right? So Google can build their own chip and they deploy it in their data center. Amazon is doing the same, Facebook is doing the same. So how that will change both the industry, and how do you think that will impact the research that is being done in academia?
Let Partha take that one.
So I think I'd like to make 2 points, right? So one, even though we have accelerators, a general purpose processor isn't going away anytime soon. I mean, Intel is still a very close partner, AMD, ARM. We work with everyone, and I think there's still going to be a space for all of that. So I don't think it's in some respects additive. And if you look at NVIDIA's recent announcement of their Grace ARM CPU and how it is very interestingly closely coupled with the GPU, I think there is this happy medium between general purpose computing and accelerators. So I think that I think this is still very early, so we have to see how all of this goes. But the other thing is also, I think we over-fixated on open source. It's open source is, yes, it's a long way there. I agree with you, Samira. You're probably right. We all have to do something as well instead of just getting excited by it as well. But it is about an architecture that's modular, right? So you can have something that is not open source, but it's all plug and play. And that's why I gave the example of ARM AXI. And so ARM licenses stuff, but you have ARM has an ecosystem. It's not open source, but it's an ecosystem where the friction to doing a bunch of stuff is much smaller. And so I think a lot of this is just a mindset in terms of thinking about our architecture. So when we write a large software distributed system, we understand that 1,000 software engineers are going to be working on it, and we make sure it is readable. We make sure that it is modular, there is documentation, it's plug and play, APIs are defined, APIs are maintained, all of that stuff. And we need to start thinking about hardware that way as well. And I think it's a little bit of a different mindset in terms of being more systematic about thinking about the modularity, the interfaces and abstractions.
Yeah, I agree as well. I mean, from my perspective, I think it's great to have more hardware vendors. Absolutely, Intel and AMD machines are there for a good reason, and they remain widely used for a good reason. I don't think that accelerators will replace completely general purpose computing. But in a way, it kind of lowers the bar of new acceleration ideas finding their way in real systems. So to give you an example, we had this work on network acceleration using tightly coupled FPGA. And I think if we had done this, I don't know, 5 or 10 years ago, it would be difficult to get excitement from industry. But because you see a lot more FPGAs and accelerators in data centers, there are several companies that have been interested in that. So I think it's a good thing to have more places where hardware design goes.
Yeah, I guess I would agree with that. And also to add on the next network acceleration. So just because the whole pipeline is open source, right? The P4 language is there, the pipeline, the math pipeline, it's already there. The FPGA implementation is available through NetFPGA. So even in my group, I think it was around a year of work to do some SmartNIC work in FPGA end to end. So I clearly see the benefit that if we can have this modular hardware, open source or IP based, that would very much accelerate the innovation. So that's actually some, I guess we should try to think about some consortium and try to get actually running. So I guess let's kind of look at the future, and I would like to know that for the future, maybe in 10 to 20 years, like what do you feel the most excited about? Like what type of problems or challenges that you think that keeps you awake in the night?
Christina, you want to go first?
Sure, I can give you an example. So, okay, I'll give you a more specific example from the hardware side, and then I'll give you a more general example. So the specific example is I'm really excited to see more tightly coupled accelerators finding their way in cloud systems. So peripherals that are not necessarily connected over the typical PCIe bus, right? So if you see, so going back to the example that I mentioned before on network acceleration, we use the cache coherent interconnect for that. And it's great to see that there's a lot of excitement around new interfaces like CXL for connecting accelerators to host machines. So that's a specific area that I'm very interested in, but more broadly, I think finding practical and scalable ways to manage complexity in cloud systems, because complexity will only continue to increase, and essentially abstracting it away from not just the end user, but also the cloud provider. That's a very interesting direction. So complexity is both in hardware and in software. So in hardware with respect to heterogeneity and acceleration, in software with respect to new programming frameworks like serverless and microservices, there is this increased amount of complexity, and the user should necessarily be burdened with handling that. So yeah, I am excited to see how much of that can be abstracted away and what are the best ways to do that.
Yeah, no, all of them sound pretty exciting. And So I'm lucky to have a vantage position where working where I do, I get to see a bird's eye view of some of the technologies and the changes. And honestly, I think there's a huge number of opportunities that look very exciting. I, I, I think pretty much every level of the stack, there is a lot of innovation going on. Obviously, at the silicon level, you have accelerators. And honestly, I think we are still very, very early in the era of accelerators. Even on machine learning, we just talked about our fourth generation of TPUs last week. And so we are 4 generations old, but there's still a lot of space there, video security. There's at least like 5 or 6 big areas where I think there are good opportunities for accelerators there. At the server level, I think, again, there's an opportunity to rethink server architecture. And if you think about it, the server has been all looking the same for decades, right? 50 years back, you look at a server, you have 2 sockets and you have a bunch of DIMMs. And now you look at a socket, it's 2 sockets and a bunch of DIMM, right? But I think the server is going through a very profound transformation. And I often think of it as you have a mini distributed system in a single computer, because you have the main compute, but you have acceleration, you have offloads, you are thinking about computational storage, computational memory, and all of a sudden you have multiple brains in a single server, and they all work with each other, and you have to manage root of trust, and you have to manage system health and so on. And it gets to be a fairly interesting challenge how you do all of that. And when you add in things like modularity of blade servers and so on, things are very exciting. And I'm on the board of the Open Compute Foundation. And one of the things we are doing is talking about some of the opportunities that it provides as well. So on the server side, there is a lot of opportunity to rethink system architecture. And then when you connect it to distributed systems, and you think about networking, and you think about the fact that you have latency that is 40 times better than what we had in the past. We have 10 times more bandwidth. You kind of have to rethink what clusters mean, right? And again, clusters have gone through epochs all the way from the internet or client server to scale out and so on. And again, I think there's a really interesting inflection when you change the assumptions by an order of magnitude. What constitutes a cluster and what you can do there, and how can you rethink system balance across compute, storage, networking? I think that's super exciting. The data center, again, is being reinvented in a lot of ways. I think for this audience, I'm not going to go into that, but a lot of super exciting stuff there, particularly around sustainability and thinking about how can we be green about our footprint, and how can we be energy efficient all the way from silicon to concrete. And then the last piece I will say is around data-centric computing. And people who know my work know I'm a little biased towards data-centric data centers and so on. And again, to me, it is always very interesting when exponentials diverge. And the rate of growth of data is exponentially diverging from the rate of growth of compute. And so every year, the opportunity gets bigger and bigger. And then I really love some of the very exciting work that some people in our community are doing. For example, Karen and Luis in UW and their DNA storage is just such a provocatively cool idea. But I do think that we are going to have to start looking at storage and storage processing and storage-centric computing. And to me, the next 10 years are going to be defined by a lot of very, very interesting challenges, but also a lot of opportunities for innovation. So pretty much across the stack, a lot of very interesting things.
You mentioned some of the data center things around, I guess, cooling that you most probably didn't want to talk about, but can you just elaborate a bit for our viewers?
No, I think, again, if you look at a data center, again, it has been pretty much traditionally, there's a bunch of concrete and you look at how you want to get things done. But again, the architecture of data centers are dramatically changing. Just if you look at the data center as a computer book and you look at, we are now in the 3rd edition, and you look at each time we define the data center, it's been very different. Last time we talked about how we are doing 48 volt medium voltage all the way there. And we had an ASPLOS paper last time, which is pretty transformational. But then if you think about how the data center is now part of a continuum where you have data center, you have on-prem, you have edge, you have various kinds of stuff. And Microsoft actually had a really nice keynote which talked about the continuum here. Google Cloud obviously has a lot of interesting things here as well. So there's a lot of really nice opportunities, and I'm seeing that show up in how you design data centers, new power technologies, the battery technologies that you see, whether it's from Tesla or anybody else, have a very disruptive effect on how you think about data center architecture. So that's very interesting. And then if you look at renewable power, Google has basically had a pledge to go 24/7 carbon free. And so when you think about what it means for data center design and so on, there's a lot of implications there. So those are kind of some of the things that I think you'll see show up in different designs soon. And they touch the computer architecture as well, because you can't really touch that portion of the system without really thinking about the IT side of things.
No, that's great. Actually, I kind of poked you to describe more because I think like for the students, it's actually good to know that like architecture nowadays means so much more than just the architecture, right? So people who are trying to look at power efficiency, battery technologies, even I guess nowadays edge computing would be kind of coupled with data center computing. So the possibilities are endless. And I guess Christina also mentioned that how data center is just changing and how excited we all are to see where we are heading. So I would like to thank you both again for giving your time and sharing your thoughts. Thank you so much. And I guess any last word that Partha and Christina, do you want to say?
Okay, I'll say one piece of advice to students that may be listening to. First, not be afraid to go outside of their comfort area or comfort zone and look for other parts of the system stack as well, because they might find connections and interesting problems that they hadn't necessarily found. And to not be afraid of jumping into a large system design project. I know it takes a lot of time and a lot of effort, and if you're the only person working on a project, it's hard, but you learn a lot of things about how systems work.
Yeah, no, I think that's good advice. I wish I had heard earlier too. And I think I'll reiterate what I said. Always focus on how your work is changing the world. And it's okay if it is one small piece, but it's important to realize how your work is finally being perceived by somebody whose life is getting better because of the work you're doing. So follow that. Sometimes it might be one step, sometimes it might be 15 steps, but there is always a connection. And I think once you do that, it gets super inspirational to be able to come into work every day and work on what you're doing, and it helps you go through some of the more challenges around being the only person to build a large system and so on. It gives you a rationale to make all the other things that need to be done as well. So really focus on the end user and the actual metric that you care about. And also wanted to thank you, Samira, for having us here. I think this whole happy hour with architects is a really nice effort, and especially with all of us remote and not being able to meet each other in conferences. I appreciate the opportunity to be able to at least reach people through video this time. So, and hopefully, fingers crossed, we'll start meeting each other in person soon.
Yeah, thanks a lot, Samira.
No, my pleasure that you found time, you make some time for participating and discussing the cool ideas that you have. So thank you so much.
Thank you.